All right, let's begin. So we've got an exam coming up. That's next Tuesday, right? Next Tuesday. And as I mentioned in our last class period, you can bring 1 page of notes, and you should also bring your computer because there's a pretty good chance that I'll include at least something on the test where you'll need access to Microsoft Excel. Today I'm going to be describing the design project, and so just to put it on your radar, the first design project submission, a draft analysis of demand inside of a hypothetical water network you're going to be designing. That submission is due on Thursday the 7th of March, and so I've got a whole handout for you, and I'm going to show you some additional resources that are online related to the design project. We're going to continue talking about pumps today. And Affinity Laws describes how pumps, when you combine 2 or more pumps together, how they behave, or when pumps are operated at conditions other than their standard operating conditions, how the performance is adjusted. Any questions related to the announcements before we begin? No? All right. Just to refresh our memory and to kick things off, let's consider this system where, remember, we identify what the flow rate is going to be by setting the system curve equal to the pump curve. And every system can have a system curve generated just by rearranging the energy equation for the parameters that you've got. So here in this illustration, it looks like we have some lower reservoir, A, and there's an inlet that the water goes through, where we're having a local loss, K equals 1. The water goes through the pump, which is adding pressure, and it has enough energy that it's able to lift the water, an elevation difference of 12 meters, and then the water exits here at C, and rather than exiting to a tank, it still has some velocity head as the water comes out of that outlet. So any questions so far? All right. What I'd like you to do is go through the process of developing a system curve. And remember, the system curve is just use the energy equation, rearrange it in terms of HP on the left side. And the reason why you're doing that, the reason why you're rearranging the energy equation in terms of HP is that you're then going to set it equal to the pump curve. And this pump curve is just given by the manufacturer, and if we look at it, what's the cutoff head of this pump curve? What's the cutoff head? The head against which the pump isn't able to generate any flow rate. If Q is 0, what's the pump head? 18 meters, yeah. So what that means is that's the maximum elevation this pump is able to lift against. And so just by a quick inspection, we can see that, yes, this pump is going to be able to generate a flow rate because we're only lifting the water 12 meters. So there are situations where if the pump curve was H sub P is 6 minus blah, 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 it wouldn't even be able to get any flow at all. But in this case, we will have some positive Q. Just the question is, what is the flow rate? And identifying what Q is going to allow you to answer this question, how long will it take to pump 1 metric ton of water? And a metric ton, that's 1,000 kilograms. So in other words, that's 1 cubic meter of water. All right. So I'm going to pause the recording. And one of the things, just to make this a little bit easier, I'm giving you a fixed F value. Of course, in reality, that F value would be dependent on the flow rate. And we went through all that last time where you start with the fully turbulent flow assumption, you develop what is the flow rate, and then you check the fully turbulent flow assumption. But just to make this more of a reinforcing example rather than the full thing from the beginning, let's start with a fixed F value. So your process is substitute everything into the energy equation, rearrange the energy equation in terms of H sub P, set it equal to the pump curve, and solve for Q. Mm-hmm.
K values 1 or the local losses are, but I think one of them ones they only have to give us a K value.
Yeah, there's a table of K values in the textbook that shows like an entrance where it's just flush with the tank, where it's going into the tank, or if there's a curved inlet. So if you've got access to the textbook, you can get some of the K values from that. You know, and maybe it would say here's a globe valve, or it could say here's a 90-degree bend. But in other instances, like in an exam, you don't have that table, and if the K values aren't given, then that kind of implies to ignore the local losses.
Okay, that helps.
Yeah. So is any Okay, so we have a system curve, and we set it equal to the pump curve. So here was the given pump curve, 18 minus 5.6 q squared, setting it equal to the system curve, and kind of subtract the numbers from one side and the q from the other, and we solve for the q. You should get 0.144 cubic meters per second. And I guess maybe just for kicks, I wanted to find out how much head is the pump adding in those circumstances. And I can substitute it into either the system curve or the pump curve once I have the Q and find out what the head is. So at this flow rate, the pump is adding 17.85 meters of head. But more to the point of what it was asking how long does it take to pump a cubic meter? That's a metric ton. For the density of water is 1,000 kilograms per cubic meter. So it'll take about 6.9 seconds at this rate to pump the metric ton. Maybe a little more if the water level in the tank is going down. Because if the water level in the tank is decreasing, then now it's having to pump against a greater elevation difference. But assuming a constant head at the source, then the flow rate will be constant. Okay, so any questions up to the point of determining the flow rate and the time? I think it's easy to get lost in the algebra, but what you need to just understand is the underlying principle is we're trying to get the energy equation simplified so it's just H sub P in terms of Q. So that it's just constants and the only unknown is Q. And then with the other equation being the pump curve, we can set the H sub P's equal to each other and then solve for that Q. Now when it comes down to efficiencies, what it was asking here is the pump is 80% efficient and the motor is 65% efficient. How much power is going to be consumed? And so, of course, the power equation, just ideally, is going to be the flow rate in terms of cubic meters per second, multiplied by the unit weight of water, multiplied by how much pump head is being added. And we had seen already how much pump head is being added by substituting the given operating point, 0.144, into the pump head equation. So we come up with the composite efficiency. Both the motor has some losses and the pump has some losses, and so the composite efficiency is 0.52, meaning that for every 0.52 watts of power that actually gets added to the water, it requires 1 watt of electricity going into that motor. And so then if we calculate the power, we substitute the operating point, meaning the flow rate that we determined earlier, the gamma for water, the pump head, and you can't see the decimal. That's 17.85, not 1,785. So that's the pump head, and then divided by the efficiency. So 48.5 kilowatts, that's a lot. Just as a matter of perspective, like your house, when the air conditioner is on, anybody have a sense for how many kilowatts your house is consuming when your air conditioner is on? Like around 5 or so. So this pump to a cubic meter. I mean, think about a cubic meter, that's a lot of water, right? And what we're doing is we're lifting that much water. How high are we lifting it? 12 meters. Lift a ton of water 12 meters in 7 seconds. Yeah, you're going to use a lot of electricity to do that, especially when you've got some big losses. So 48.5 kilowatts is the rate of energy consumption when you're lifting that water. So you'd need some big power lines going to whatever facility is doing this pumping. You probably wouldn't be able to do it just with the 110 extension cord. It would just melt long before you could deliver 48 kilowatts through just a normal extension cord. Okay, it's just a matter of practice on these. You know, this is only the second maybe pump problem you've seen. I think you'll have some more in the homework, but it takes practice to feel comfortable with it. So I encourage you to get that practice. All right. Affinity laws, sometimes called scaling laws, are used to describe what happens when you have like a series of pumps that have a similar shape and similar performance but slightly different size. And so oftentimes a manufacturer will have a certain style of pump that comes in like an inlet diameter of 1 inch, 2 inch, 4 inches, 6 inches. And so all they're really doing is they're scaling up the size of the impeller vanes and the size of the inlet and the outlet. But a lot of the characteristics are similar within that series. These scaling laws can be used to tell you how the system is going to behave when you switch from one pump to another. Or if you have a pump that's normally operated at one speed setting, but then you change the speed setting, then you can use the affinity laws for that as well. So here are the equations that allow you to predict in situation 2 what's going to happen with the pump that was behaving a certain way in situation 1. So here's what the 2 and the 1 is meaning, is kind of under one set of circumstances versus another. And you wouldn't need to solve all 5 of these equations simultaneously. Sometimes what you're doing is you're putting a given pump into like a different rotational rate, and you want to know how is the flow rate going to be different if you change the rotational speed. So you can see here, rotational speed is assigned this variable n. And so if you have a pump where you're going to be, it's the same diameter pump as it was before, but now you're operating at a different rotational speed, you can use this to understand how the flow rate is going to change. Or if you want to predict how the mass flow rate is going to be adjusted by changing the diameter, but you're still operating with the same electric motor, so maybe you're spinning at 1200 RPM, but now you've switched to a different diameter pump. So you could then use this second one to predict how the mass flow rate would change between situation 1 and situation 2. So these are the scaling laws, and you can find these same equations in the FE reference manual. And to give you an idea of how these scaling laws operate, we're going to consider the case of a pump that normally uses a 1200 RPM motor and an 8-inch impeller. So the manufacturer of this pump can give you either like a sketch of its performance curve or an equation that describes how the pump head decreases as the flow rate increases. And so that's the performance curve that we've got. At 1200 RPM, this is what the pump is able to do. And so as a cutoff head of 12 meters, which means if you're trying to lift water any further than 12 meters, this pump will just kind of be spinning its wheels, so to speak. It won't be moving any flow. We're going to use the affinity laws to consider a couple of different possible changes. In the first case, we're going to look at what happens if you use what's known as a variable frequency drive. And so you have a variable frequency drive, and you're trying to spin this pump, which normally goes at 1200. You're going to spin it at 2400 RPM. And so we want to know what's the performance curve in that situation. Okay, so for part A, I'll show you one, and then I'll let you try part B and C on your own. So for part A, we want to change to 2400 RPM. All right, so that means N2, which is the rotational rate under the second condition, is 2400, whereas the N1 was 1200. That was the original rotational speed that it was going. Both D1 and D2 are the same. So D2 it's still an 8-inch impeller as it was originally. And what we want to do is find H. So H2 is going to be like the pump performance curve. So what we have is our original pump performance curve. H1 was 12 minus 0.1 Q squared. That's what it would do when it was spinning 1200 RPM. And we want to find out what is the equation for how the pump is behaving when it's spinning twice as fast. Okay, so if we go to the affinity laws and we try and find out which of these equations are we going to use, we want to find out what is the ratio of the Q's, and we also want to find out what's happening with the heads. Now, this problem isn't speaking to a mass flow rate or to the power consumption or to the pressure rise, but the two of these pump law equations we're going to use is the top one and the middle one, because we've got a change in Q and we've got a change in H. And so this H1 was under flow rate 1, and we want to find H2 for Q2. All right, so the first one, the affinity law that we're using is Q divided by N D cubed, and all that's for condition 2, is equal to Q divided by N D cubed for condition 1. Since the diameters are the same, we can simplify this. So it simplifies to just being Q2 divided by N2 is equal to Q1 divided by N1. In other words, the ratio between Q1 and Q2 is Q1 is N1 Q2 divided by N2. Okay, so 1200 RPM was our original rotational rate. Q2 is still unknown, and N2 was the secondary, the after rotational rate, and that's 2400. Okay, so what that tells us is that Q1 is 0.5 Q2. So that's just saying that the effect of doubling the speed is that the flow rate ratio is that the second flow rate is going to be double the first flow rate. But the head situation doesn't scale quite as simply as that necessarily. So what we're going to do now is take this and substitute it in to the other affinity law. So we're going to substitute it into that middle one. So let me just erase this stuff that was up here at the top, the constants. Okay, what we're going to do is substitute it into H2 N2 squared D2 squared is equal to H1 N1 squared D1 squared. Okay, again, the diameters are equal. D1 and D2 is the same. So then what this simplifies to is H2 divided by N2 squared is equal to H1 divided by N1 squared. So what we're going to do is put in the ratio that we're going to calculate with the actual rotational rates. So we want to have H1 in terms of N1. So H1 is N1 squared H2 divided by N2 squared. So that's 1200 squared H2 divided by 2400 squared. Okay, I'm going to erase this stuff down below. Hopefully you've got that already. So what that simplifies to is that H1 is 0.25 H2. I guess I should have boxed that, not this intermediate one, because what we're going to substitute into the original pump curve are these two expressions. We know now Q2 versus Q1. We know H2 versus H1, and we can put it into the original pump curve that we were given for this first situation. So this is what this pump is able to do under the first circumstances. And so the original performance curve was H1 is equal to 12 minus 0.1 Q1 squared. This was the given. And so what we do is we substitute in these relationships between the first condition and the second condition. So in other words, 0.25 H2 is what we've substituted in here for H1. And then we have 12 minus 0.1, and then we make the substitution 0.5 Q2 and square that. So we have to divide everything by 4 essentially. If we rearrange that, it's going to be H2 is 48 minus 0.4 and then times 0.25 Q2 squared. So we're squaring what's inside of those parentheses, the 0.5 Q squared. So in the end, when we finish simplifying everything, H2 is 48 minus 0.1 Q2 squared. So this is the new pump performance curve if we spin that original pump twice as fast as we did before. This is one of those cases where I really wish that we had a much larger whiteboard because I had to erase things and it wasn't well organized. So let me just scroll through it here on the screen so that at the very least you've got a recording of that solution. So what we wanted to do is we wanted to find out for the original pump conditions, originally 1200 RPM, the original H1, which is the pump head that it's adding at a certain flow rate. We want to find out, instead of spinning it at 1200, what if we spin it at 2400? So we find the relationship between the flow rates, find the relationship between the head amounts, and then substitute those two equations into the original performance curve and get the new performance curve. So this one tells you what happens if you spin it twice as fast. In the second example, just to give you some practice with this, what if the performance curve of the original same rotation rate, but we change to a 10-inch diameter impeller? Okay, so now N1 and N2 are equal. We're changing the D values. Okay, so go through this same process that I went through, but This time it's a different D. D1, the original diameter, is 8. D2 is 10. So think about, we're essentially doing the same thing, but instead of changing N, you're changing D. So you're going to have this first phase where you find the ratio of the flow rates, Q, and then the second phase where you're finding out the relationship of the H values, and then you'll substitute both the Q relationship and the H relationship into the original pump head equation. But this time what we want to do is we want to say we're going to have a 10-inch diameter impeller. All right, so in part B, we're going to spin it the same speed as it originally was spinning, but we're going to use a different diameter tube inside of the impeller and the entry and the exit. So it's basically just scaling up the size of the pump. Originally we were using an 8-inch, but now we're going to switch to a 10-inch. And so the question is, how does the performance change? In this first part, what we saw is that by spinning it twice as fast, you go from a cutoff head of 12 meters. You don't double the cutoff head, but rather you get 4 times the cutoff head by spinning that impeller twice as fast. And so that was a pretty significant change by, to get it spinning faster, you're adding a lot more energy, but then you're getting a different level of performance out of it. So the question is, how do things change if we had the original cutoff head of 12 meters? How do things change if you just basically scale up the pump? And you do get a little bit more cutoff head, but not nearly as much as spinning the original pump at twice the speed. So when we make the ratio between the original flow rate and the flow rate under the second conditions, here we find out that that ratio is going to be 0.512. So the Q2 is bigger than the Q1. And so is the ratio of the heads is changing. And then you substitute it into the original performance curve to find the modified performance curve. And so this is what we get. The question, the kind of concept or thought question was if you need to pump water 30 feet above the original source, which option is best? And so I guess I've been saying meters. Let's assume that the cutoff head is feet rather than meters. So if you want to pump 30 feet above, this second situation of increasing the diameter wouldn't do the job. It would only be able to lift water a maximum of 18.75 feet. And even if you're lifting that far, you're not going to have any appreciable flow rate. But this one can lift 48 feet, and it'll still have the capacity. If you lift 30, it'll still have enough energy to actually achieve some Q. So the answer to this part C is the 2400 RPM original pump would be better. Okay, so those are the affinity laws. The next note in the slides, I'm going to come back to at a later date. This is to reintroduce the idea of Watergems, which you had just the briefest exposure to in the fluid mechanics course, but you're going to be using Watergems in the project for the second phase, not for the first phase. And so probably what's the most useful thing for me to do as far as this example is I'll send out a reminder email to everybody on how to get Watergems if you don't already have it installed on your laptop. And then we'll work through this example together the day after the exam. So we've got the exam coming up during our next class meeting on Tuesday. So bring your computer to use on the exam on Tuesday, but then on Thursday, bring your computer loaded with Watergems so that you can work through this Watergems example with me. And what we'll essentially be doing is duplicating this same example that we worked with the Hardy-Cross method. You know, we solved this one on the spreadsheet, so we're going to see how well does the spreadsheet style solution match up with what Watergems does. So instead, let's talk straight about the design project. I've given everybody the map already. Let me give you next a handout that says what your design assumptions are going to be. By the way, all of these materials are available on MU Online. If you accidentally lose one of the papers, the PDF is online for you. You'll find your name on this handout, and you'll see what city you're going to be assuming for this development. Essentially what this is it's a piece of land that doesn't have anything on it right now, and they're going to have some residential developments put into this land, some commercial areas, a few industrial zones, and what you need to design is a pipe network that can deliver enough water to satisfy the demands at each of these green arrows. So at each of the green arrows is a spot where you need to provide water, and the pipes don't have to go in any particular location necessarily. If you like, you can follow the perimeter of this this boundary. You know, you can think of this as the interior section that's going to be developed, and then there are a couple of exterior features outside of the main developed area. But for each of you, you have an assumption I've told you on what to assume for the residential population density in each of these zones. Some information about how many people will be in the sports stadium and how many hospital beds there are and the size of the housing project and so on. And so oftentimes in engineering design, before you do like the full finished plan that you're going to take to actually construct in the field, it's fairly common to do what's called like a 30% design. And in a 30% design, you're just kind of doing a quick placeholder design so that you have a rough idea of how big things are going to need to be. And you do that planning really to get an idea of what the scope of costs would be for a development. And so if this is some raw land that needs to be developed, you can assume that you've been hired by the land developer to identify what the pipe network should be to make sure that there's enough water at each of these locations. And of course there's going to be secondary pipes inside of the network, but probably whoever's putting in the neighborhood would be in charge of putting in those secondary water lines. You're just providing like the main stem of the services. What you'll notice is that the water comes into the network here at junction A. That's the one place that the water comes into the network, and where it's coming from is there's a spring here on the map up by the number 300. I think maybe on your map there's a strange little symbol there. That symbol identifies the spring. And your map, by the way, is scaled such that 1 centimeter on the paper should equal 100 meters in this planned development. So if you measure that black line, I'm hoping the printer scaled it correctly, and that black line would be 1 centimeter in length, and then that's going to represent 100 meters in reality. So later on in the project, I tell you a little bit about what to assume for the amount of water that's coming from the spring. But the questions that you're going to face in this project is, how much water do people use? Because it's easy as an engineer to oversize infrastructure, just to make the pipes gigantically large and they'll always be big enough. But the problem with doing that is that it's not efficient and it's not considered optimized. You'd be providing maybe enough pressure, but you wouldn't be doing it economically. And so in the project handout I'm going to give you that kind of gives an overview of the assignment, it explains that what you want to make sure is that during the peak flow condition, everywhere in your network has at least 240 kilopascals of pressure. And the way you're going to pressurize your network is you're going to put a reservoir somewhere up on this hill. If you know how to read contour lines, what you'll notice is that the town is sloping downhill in this direction. So this is uphill, and somewhere on this hillside you're going to place a tank of water to pressurize the network. And if you look around in this area, you'll see that same exact thing. There's big green tanks on hillsides, and that's what provides pressure into people's homes. So you want to have the tank high enough that you provide enough pressure when people are using the water, that there's always at least 240 kilopascals, but you don't want to have too much pressure because during the low flow times of the day, the pressure shouldn't go any higher than 850 kilopascals. And that maximum pressure kind of corresponds roughly to the ability of water heaters and other fittings to not leak. So you want to leave yourself a little bit of a safety factor so that welded joints don't begin to leak. So the design project has 4 different phases. Phase 1 is demand estimation. And so what you're going to do is, based on the information that I've given you, you're going to make some assumptions and calculations and try and figure out how much flow is required at each of these points. So, during the design condition, which you can assume, like it's the worst case scenario, when this entire land is fully built out. So it's a mistake to design your infrastructure for the demands at the beginning of the project life, when no one has actually moved in yet. You want to think many, many years in the future, 25, 50 years in the future, when this is fully built out. You want to make sure that the pipes are big enough to satisfy the peak demands during that time period. So number 1, it's going to be in the future. But number 2, think about seasonal variations in water demand. Now, how do people's consumption of water vary from month to month? And then also, how does it vary day by day? This is a figure that's included in some resources I'm going to give you that kind of illustrates the daily variation in demand. And so what you can see is that during the nighttime hours, even on the maximum day of the year, which maybe is during the summertime, even during the maximum day of the year, there's this nighttime lull where the demands are a little bit lower than the average day would be. So 100% here represents the average demand on the average day. So on a typical winter day, the demand is going to be less than the average demand on the average day. But then on the maximum day of the year, you might expect to see like 275% of the demand during the average day during this high peak time nearing 8 o'clock. So what you're going to be calculating is a couple of different demands. First of all, you want to consider what is the maximum daily demand that you could expect to see, and you're also going to calculate the maximum hourly demand. And there's some peaking factors that you should use to do that. You're going to calculate, the average consumption of water inside of your network, and then you can scale it up with a 1.8 times multiplier to find out what's the maximum daily demand compared to the average day. and the maximum hourly demand would be 3.25 times as much. And the reason why you're calculating both is that one typical design standard would be you want the pipes to be big enough to satisfy either the maximum daily demand plus any kind of fire consumption requirements or the maximum hourly demand, the larger of those two. And by the way, all of this is described in the assignment handout. Let me give that to you now. I've been doing this project or something similar to it for about 12 years now, and it's evolved over time. I've in some ways made it a little easier, in some ways I've made it a little harder. When the students first started this project, they didn't have Watergems. So they were doing like an iterative pipe design without the ability to just snap their fingers and automatically analyze what's the pressure every place in the network. So in some ways you're really spoiled in your ability to iterate the pipe sizes and really quickly calculate how things have changed. There's a lot of information here. I'm not going to stand up front and read all of this to you. But I will tell you this. I get a lot of questions from students who clearly haven't read the handout. And when I get questions like that, I'm glad, on the one hand, I'm glad they're asking questions because I'm always eager to help. But then on the other hand, I'm a little bit disappointed because it shows that maybe they're not taking the assignment as seriously as they should. So what I'll say is schedule some time for yourself to read all 3 pages of this handout and do it early because you may want some of the thoughts to percolate and some of the ideas to sink in before you actually have to put pencil to paper and start doing the calculations. So one aspect of this project is looking at how the demand varies over the course of a day and thinking about, well, how much water do they require in a hospital? And so just as an illustration of what kind of data is out there, I'm now on the course page for our course. There's a new folder called Design Project Resources. It's at the top of our list. And if you click on it, it's going to have the assignment description I've just handed out. In case you forget what your parameters are, that's there. And there's this third PDF file is Demand Estimation Example Resources. And so this is just showing an example of in Davis, California and England, like the month-to-month precipitation versus the evapotranspiration. And you may be wondering, well, what's that all about? I'm providing that because one of the things in your town is a golf course. So golf courses require water to irrigate during the dry season. And so this is showing, for Davis, California, what you could do is you could find out the difference between the monthly average precipitation and the monthly average evapotranspiration, like how much water is being lost by plants. So I'm not sure if anybody here is assigned Davis, California, and I know nobody here is assigned England, but this is an example of the kind of information that you'll need to go out and find online. So you can use some of this just directly. For instance, let's see. Typical municipal water use in the United States. This is a good one. So this is saying that the average demand of water in terms of liters per person per day. In the United States, the average demand is 220 liters per person per day. So one of the notes that I give in the, let's see, let me go back for just a second here. Right underneath these example resources, you will not earn 100% of the available points if your demand estimation is solely based on the example resources that are provided. For full credit, additional analysis and outside research is required. So what I mean is, you can just use this 220 figure if you like, the national average, but you're not going to get, you're not going to wow me with like your outside effort and the research depth that you've done. But if you're assigned Las Vegas, Nevada, and then you go online and you find out for Las Vegas, Nevada, how much water do people use there? And rather than using the nationwide average per person demand, you go and find the actual demand for your place. And then you'll notice one of the parameters on this table that I've given you is the population density. So on the map, if you know that this particular section, the north zone, is 50 hectares, and you've got 150 people per hectare, okay, that tells you how many people are living in here. And then you can go to a data source like this and find out the number of liters per day that people are using. So you can find out how many liters per day is required inside a certain part of your network. So here in the north zone, you now have an idea of the residential demand for water. You'll notice that the north zone is fed by two different arrows. This green arrow here at A feeds the north zone, and so does the arrow at M. So each of these interior sections is fed water from just two of the green arrows. And what you can assume is that it's split equally, that half of the demand in the north zone is fed by junction A, half is fed by junction M. Likewise, in the south zone, half of the flow interior to that zone is delivered by junction L, half of it by junction O. And of course, there's these exterior water demands that are provided separately. So what about a sports stadium? How much water do they need at a sports stadium? Depends on if we're talking like soccer or, a sport that people want to actually watch. All right, so there's some information in here, that tells you where that 220 liters per day comes from, by the way, if you're wondering, what's the breakdown. Here is some different types of facilities, like airports, how much water is required on a per passenger basis, a motel on a per person basis, a shopping center, hospitals, prisons. It's funny that the prisons require so much water. I wouldn't have thought that. I've never been to prison. All right, so go through here. I think you'll find some interesting information that can inform your demand estimation. What you're going to submit on Thursday, March 7th, is a report where you're showing me all of your calculations, and then you're summarizing your calculations in a very specific pre-formatted way. Let me give you the handout of what your summary table needs to look like. I have a rough idea for each student. I have a rough idea of what's a reasonable demand. But of course there's a range depending on your assumptions. And so what you're submitting as the draft for this demand forecasting is your calculations that tells me how much water is used on an average day basis for residential and commercial demands inside the north zone. And then the format of this table, as you read through the assignment description, you'll see why I formatted certain ways, things the way they are. If you calculate the average day, then the peak day is going to be 1.8 times the average. The peak hour will be 3.25 times the average day. And then you'll combine, in any place where there's a residential demand, you're going to find out what is the peak day plus fire flow. And then the design flow is going to be the combination of either the peak flow during the highest hour or the peak day plus the fire flow. So you'll notice, see how there's not a box here for commercial demand, peak day plus fire? There's no box there because in the commercial areas you assume that they have sprinklers, and so then the demand isn't based on the fire flows there. The design demand in the commercial area is just based on the peak hourly flow rate. So this is set up in this way for like a specific reason, and I think that as you read through the assignment description and start doing your calculations, you'll be able to start filling in the blanks. And one of the things that I want to draw your attention to on the assignment description is how I grade this project, because I intend it to be, I've broken it up into pieces intentionally so that you're able to make adjustments if you have a mistake. And I've carved it up into pieces so that this isn't the sort of thing that you're panicking at the end of the semester trying to put together in a panic. Break it up into pieces so that here for demand forecasting, for example, it's 30% of the project grade, but only 15% is at the draft stage. And so if you really miss the point of a whole assignment and you do your best, but it's really wrong, then I'm going to give you that feedback soon enough that you can make changes before it affects your pipe network sizing. And then I'm going to look at your design of your network, and I'm going to give you that feedback before you size how big the tank has to be up on the hillside. And then you'll have all of that feedback before you start doing like a cost analysis and putting together the finance options. And so it's broken up into phases. The demand forecasting is due on March 7th. Then the second phase of actually designing your network in Watergems, that's on March 19th. The reservoir, April 9th. And then the final project report is due on Tuesday, the 23rd of April. So that's a couple of weeks before the end of the semester, because I like to avoid conflicts with other projects you might have going in other classes. But I try and break it up into digestible pieces so that you're getting feedback early enough and often enough that I give out lots of full credits on this project, because people put effort into it, they do a good job, they make corrections when necessary along the way. So this is generally something that brings the grades up. So what I really encourage you to do is read through this, and we'll conclude just by taking a look at the announcements. Remember that when we get together on Tuesday, we're having an exam. Your homework assignment is due before that exam, but then also bring your computer a week from today so that we can go through Watergems together. All right, I'll see you on Tuesday.